back, and let's talk about the primary types of bonding that we're going to be dealing with in this class. Specifically, we're going to break it down into two sections: intermolecular and intramolecular bonds. So we have this. Hopefully, you remember your either Greek or your Latin roots. Inter is going to be basically between. Intra is within. So we are going to deal first with intramolecular, within. So like not between, basically, molecules or arrangements of atoms, but we're going to deal with within. So intramolecular interactions. So all the interactions that we're going to talk about here are intramolecular. So intramolecular interactions. So we are going to be dealing, again, we've kind of mentioned this previously, but valence electrons are incredibly important when it comes to bonding. So if we have no valence electrons, if we're, are inert or noble gases, so we kind of saw them previously on our periodic table. So our noble gases are right here: helium, neon, argon, krypton, et cetera, et cetera, et cetera. Those atoms, they have no valence electrons, but valence electrons are going to be incredibly important when it comes to bonding. And bonding, again, is it's our atomistic length scale. It's going to kind of determine all these different structural, physical, and chemical properties. So in this interatomic bonding, this intramolecular bonding, we're going to have basically three types of intramolecular bonding. So it's going to be covalent, ionic, and metallic. And I want to point to you these values. EV, electron volts, that's an energy, essentially. So it's essentially the energy to break these types of bonds. Now, these are just generic values, or not generic values, but typical values. In material science, one of the things you'll learn is that there's always an exception to every single rule, whether you like it or not. But the other way that I kind of like to denote and write the energy of these bonds, you can see that generally covalent is stronger than ionic, which is stronger than metallic. And we're going to see, actually going back into the course, that so for a lot of the super stiff materials like tungsten, for example, which is the stiffest material, has the highest melting temperature, it is covalently bonded. It's ceramic. Ionic materials like NaCl, and then metallic materials like copper, titanium, et cetera, et cetera, et cetera. Now, you'll see this other notation of Kt. What does this mean? Well, this K is our Boltzmann's constant. So, Boltzmann. That is 1.23 times 10 to the minus 23. Actually, 1.28. 1 second here. As you know, I'm going to have to double check my Boltzmann's constants. Let's see. Actually, excuse me, 1.38. So 1.38 times 10 to the minus 23 joules per K. Not going to make too big of a difference there on Boltzmann's constant. So that's kind of, this Boltzmann constant, this K is going to be, 1.38 times 10 to the minus 23. I knew it was the other value. Anyways, so you'll see that this value is 200 kT. What that means is it's going to take 200 times the Boltzmann constant, where T is equal to our room temperature. So 300 K approximately. Really 298 K, but again, we're material scientists. We're dealing with order of magnitude changes. We're not really concerned too much about those other values. So, or those 2-degree difference. So this is saying that it's going to take 200 times basically the available thermal energy at room temperature in order to break these bonds. Same thing with ionic, 80 times, metallic, 20 times. So these bonds are effectively permanent, the covalent, ionic, and metallic. You can't break them at room temperature. So you either have to, break your kind of inspiron sample and fracture it like this, or you have to kind of melt it and heat it up, and then you could kind of break, essentially destroy those bonds. So these are not reconfigurable. They are not going to reform or reconfigure at room temperature. Now, some of these other interactions, like van der Waals here, these are intermolecular interactions. Intermolecular. What are van der Waals interactions? Well, one of the best examples that you could kind of see is van der Waals are very, very weak interactions. So for a polymer, for example, this is polyethylene. Actually, we're going to get into kind of the structure of bond in a second. But van der Waals interactions are kind of quantum mechanical in nature, and they're produced by these kind of fluctuations in your kind of electron cloud. So if I have a polymer like this, so this repeat unit continues forever, and if I have another polymer that kind of wraps around here, and I have my C and then H here, even though these H's are really non-interacting, they're not polar. There's lots of other intermolecular interactions. So there's polar interactions. There's dipole-dipole interactions, there's H bonds, so H bonding. So if you see this amide group, that's kind of a clue that hydrogen bonding can occur, just like we kind of saw in Kevlar. But all these interactions are typically, again, on the order of or less than 1 kT. So around 0.2 kT is very, very adept. So they're really relatively weak interactions, but again, these interactions as they get closer and closer together. So as polymer chains or as these kind of van der Waals interactions, as they get closer and closer together, the force actually decays as 1 over I think r to the 6. So they scale like that. Extremely, extremely, extremely. I can be wrong on that van der Waals scaling. We could actually go and look at my Mach 202 notes for a second. A quick digression here. I want to just be sure of that before we. And actually, we could look at some more. Where are we at? Inter and intramolecular interactions. Here we go. Now we're getting to the good stuff. So that's my intramolecular interactions. Here are my intermolecular. So D to the minus 6. Oh, Josh, I mean, I'm so good, students. I can't. But anyways, so let's go back to our course. So these are weaker interactions, but again, they scale and they could be, they could be very, very impactful interactions. Actually, van der Waals interactions are responsible for how geckos stick to walls, if you can believe it or not. There's millions and millions in this kind of hair of the gecko structure. It's unbelievable. So these are the two types of kind of interactions that are, intramolecular and intermolecular interactions that we're going to kind of deal with typically. Now, I want to pose a question to you. Why do we even need bonding in the first place? Or why does bonding occur? Well, hopefully you've seen this equation. If you take my polymer class like we just saw in the notes, this is the fundamental equation that's required for everything in that class. And it's this continuous battle versus the change in enthalpy versus the change in entropy. We always want to maximize entropy. We want to minimize this enthalpic. We want favorable interactions. But the biggest thing is we need delta G to decrease always. If delta G is decreasing, then that reaction is not spontaneous. We always want to lower energy. So the fact atoms bond is because they lower energy. They essentially, bonding has favorable enthalpic interaction. It causes delta H to decrease. And you can see in this equation that's going to cause delta G to decrease. So the energy set of the bonded atoms is lower than that of the isolated atoms. That's I think the key idea here. And there's forces of attraction and repulsion between electrons and protons, and between protons and atoms, and etc. And hopefully you remember back from physics that the force is related to the negative gradient of the potential. So U is your potential energy. So potential is just some energy. And hopefully people know or have seen this mathematical operator, the gradient. So if I have a gradient, it's basically saying take my d dx, my d dy, d dz, take the partial derivative with respect to whatever you're kind of dealing or you're working with. So you'll kind of see this option. If we have a 1D system, it'd be du, for example. We're going to see actually an idea in a second. So there's lots of different equations and potentials that describe bonding that's going to occur. And one of the most famous potentials that you are going to run across with, there's Morse, there's Born-Meyer, van der Waals, but the Lennard-Jones potential is an incredibly, incredibly popular one, specifically for simulations. Why? Because it's computationally very, very simple. So if we have a pair of neutral atoms, we can approximate basically the Lennard-Jones potential as the following equation here. So where eta is this depth of the potential well, sigma is the distance where it's at 0, and you can kind of see this r and kind of these functions here. So we're going to vary. You're going to plug in this value and this value here, and rm is just the distance where the potential is minimized. Again, you can just rewrite this function, but these are values that you're typically given. So sigma is a fitting function, and so is eta. So you're typically given these values here. You approximate them based on the potential or the interaction that you're trying to approximate, essentially. So it's very computationally simple because you only have two fitting parameters. So let's look at this potential. So when my atoms are far apart, what's my energy? Well, they're so far apart that they really can't even see each other, interact. So the energy is pretty close to 0. And then you see that as I start to come together, the energy starts to decrease. And then I hit this point where I'm at this minimum. And that's where, again, my electron clouds and the atoms are at their equilibrium distance. Their electron clouds are overlapping. That's favorable. Again, we're minimizing energy, but they're not kind of too close to each other yet. But pretty soon, if you keep decreasing the distance, now our atoms, our neutral atoms, are starting to overlap. Those protons in the protons in your nucleus, they start to kind of repel each other, and then this is our potential. This is our energy. It starts to increase. Increasing energy is very, very, very bad. So that's the key concept that we're kind of seeing here. So on this side of the curve, right here, we are attracting. On this side of the curve here, we are repelling. And we could tell that by taking the derivative of this function. So if we take the derivative of our potential, dv dr, we set it to 0, we could figure out what is this distance, what is this equilibrium REQ right here. And we know that anything greater than REQ, that those atoms are going to attract. Less than REQ, they're going to repel. I can also tell where the distance, we had this equation here, negative gradient of the potential. I can also tell where my force is maximized. So my force maximum is just the negative of the potential. So I'd have to do, to find out where force is maximized, I'd have to do negative the second derivative of my Lagrange's potential and set it equal to 0. So that's one option as well. And then that's, again, when the second derivative is 0, that's the change in inflection point, right? So we have negative curvature here, positive curvature on that side. So hopefully that'll be helpful in your problems there. A quick little hint. So next time we're going to go into distinguishing between types of bonding by electronegativity. So we're going to break apart these intramolecular interactions and see what's what. All right. Bye.